So another concept that I touched on slightly in the last video is on conditional probabilities. A conditional probability is a probability that an event will occur given that some other event has already occurred. So we write this as the probability of A given B, or you can use a slash, or you can just use the words probability of A given B. Um, and so if we're looking at this, let's say we grab two cards drawn from a deck. What is the probability that the second card is a king, given the first card already was a king? So the probability the second card is a king, given, again, that's what that slash means, the first card is a king. Well, if that first card was a king and we didn't put that card back, we pulled two cards and we didn't put one back, so that means that that first card was a king. That means there's actually not 4 kings in the deck anymore. There are now only 3 kings in the deck. There's also not 52 cards in the deck because I pulled one card out. There's now only 51 cards in the deck. So the probability that the second card is a king, given the first card is a king, is 3 out of 51. And then let's say we want to know the probability that the cards are both kings. So the probability the first card is the king and the second card is the king. Again, you're going to multiply the probability the first card is the king times the probability the second card is the king, given that the king was actually on the first. So there are 4 cards in the deck that are kings out of 52 cards. So the probability the first card is a king is 4 out of 52. The probability the second card is a king, given the first card was a king, is now 3 out of 51. So you get 12 out of 2, 6, 5, 2, or you can leave them as the 2 out of these two just multiply together, write them that way. You can write them as a multiplication, you can reduce them, you can write them a decimal or percent. So this actually gives us what's called the multiplication rule for probability of dependent events. The probability of A and B is the probability of A times the probability of B given A. Or you can think of it as the probability of A and B is the probability of A times the probability of B given A, because the order doesn't matter. So as long as this here and that there are exactly the same, you're good. So if you've got B here, then B there. If you put A here, then it's A here. Another way you can do it, you can find the probability of a conditional probability by using the probability of A and B over the probability of A. So you're just solving for this one by dividing through by the probability of A. Again, I don't like using this. I like to prefer to just think about what would be happening, what would be the probability of this happening. So I usually don't like to use formulas, but they're there if you want them. So let's say as an example, a small parking lot has 5 black cars and 7 white cars. I'm sorry, I wrote 74, but this is number 75. So this should be a 5. All right. So this is number 75 in the textbook. So a small parking lot has 5 black cars, 7 white cars, 3 red cars, and 4 blue cars. If the 2 cars leave in random order, what is the probability that a red car will leave first, followed by a black car? So we want to find the probability of red and black. The red is going to leave first, so we're looking at the probability of red card times the probability of black card, given that a red car has actually left. So there are, if we look up in here, there are 3 red cars. So there's 3. If I add 7 plus 5 plus 3 plus 4 together, I get there's 19 cars in the deck. I mean, not in the deck, but in the parking lot. So there's 3 that are red out of the 19 cars. So now that car has left. So a red car has actually left. And now we're looking at the probability of a black car, given that a red car has left. Now there still are 5 black cars in the parking lot. So that doesn't change. What does change is there's now only 18 cars in the deck, and not deck, but in the parking lot, because that car has left. So 19 was before, but 1 car left, so now it's only 18. So it's 3 out of 19 times 5 out of 18. Again, you can multiply them together, or you can leave them just like this. I don't care. And if you want to reduce them, you can. Again, I don't care. and make them into decimals. It's really your preference. Another example is a real estate agent has kept records on the number of bedrooms in a house he has sold for the last 5 years. The data is listed in this table. It's a little hard to read, so you can also find this in the textbook, which might be a little bit better place to go look so you can read what it has to say. So we would like to know the probability of getting 3 bedrooms given that the house was sold in 2012. So in 2012, so we're looking at 2012, and so 2012 means I'm in this row. So out of this row, there are 54 houses that were sold that year by this person. And in that, there's only 16 that had 3 bedrooms. So it's 16 out of 54. We don't look at the total number of houses that he sold in all the years. We just care about 2012 because we are told that the house was sold in 2012. Let's say part B is the probability the house has 5 or more bedrooms given that it was sold in 2009. So again, I'm given this information. Oh no, I'm not given. Sorry. This is the probability of 5 bedrooms and sold in 2009. So because I'm not given any information, I am going to use the total number of houses he's actually sold, which is 258. Because I'm not given any information, I don't know what year the house was sold. I want to know the probability that it has 5 or more bedrooms, which is this row here, and that it was sold in 2009. I don't know for sure that the house was done that way, but that's what I'm looking at. So we are looking at 5 or more bedrooms in 2000 and sold in 2009. So that would be that there's three houses that were sold in that year that had 5 or more bedrooms out of the 258, because we weren't given information. We don't know anything about that house. We're looking at all the houses and what's the probability that it had 5 bedrooms and was sold that year. So this is different. It's not a given that information. It's an and statement. Find the probability of 4 bedrooms and sold in 2013. Again, we're not given any information, so it will be out of 258. 4 bedrooms is this row here, and 2013 is this number here. So looking at that, we find that there were 28 homes that were sold had 4 bedrooms and sold in 2013 out of all the bedrooms. The last one we might look at is the probability that a house was sold in 2011 given that it had 4 bedrooms. So I'm now told something about that. I'm given some information. I'm told it has 4 bedrooms. So out of those 4 bedrooms, there are only 133 houses that had 4 bedrooms. And I want to find the probability out of those, so I know that it had 4 bedrooms, that it was sold in 2011. So 2011 in this row happened to have 28. So my probability is 28 out of the 133 because I know the house had 4 bedrooms. So once I have that given information, I can reduce my sample size down. If I don't have any given information, I'm just looking for probabilities, I have to do it as a 258.